Hello, welcome back. So we're going to continue our ultimate fantastic review for the AP exam. Today we're going to go over the BC 2012. And the first question we're given is a function G has all derivative of all ordered, and the Maclaurin series. Now it says it's a series, so let's take a look here. Remember, series are always going to have that plus dot 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 at the end, is given by this. And then there's our series. The first question says, using the ratio test, determine the interval of convergence for this Maclaurin series. So ratio test, they're telling us what to do here, which is nice. And we're looking for the interval of convergence, which means in this case, we have to check the endpoints. So let's go ahead and get started. When we do our ratio test, we're looking at the limit as n goes to infinity. Remember the ratio test, if you forgot that, that is the limit as n goes to infinity. And we're going to take this, the absolute value of a sub n plus 1, divide that by a sub n. And we want to know what this is equal to. Now, for interval of convergence, we want this to be less than 1 to guarantee convergence. So over here is our series. We're just going to plug it in. We don't have to worry about the negative 1 to the n because when we take the absolute value, it just goes away anyways. So we're only going to be looking at this part. So we have to put n plus 1 in for each of those. You can verify this. So if we plug in, first we're going to take this x, we're going to get this 2n plus 1 plus 1 over 2 times n plus 1 plus 3. And then we're going to invert and multiply here. And that just becomes, we're going to invert multiply the a sub n. So that becomes 2n plus 3 over x to the 2n plus 1. And we want to make sure that that's less than 1. So I can go ahead and simplify this if I want to. The bottom here, I'm going to do this in a different color here though. The bottom just becomes 2n plus 5. And the top here just becomes x to the 2n plus 3 right there. And now I'm just going to simplify this. Let's go back to black here. So we would get the limit as n goes to infinity. If I look at the x's, we get 2n, we have this 2n plus 3 over 2n plus 1. That's going to just leave us with x to the x squared here on top. On the bottom, for the end, excuse me, we have this 2n plus 3 and this 2n plus 5. Unfortunately, there's not much we can do with those. So we are going to leave those alone. We get 2n plus 3 here, can't simplify them, over 2n plus 5 on the bottom. And again, that has to be less than 1. Keep simplifying here. I can factor out this x squared here. And if I factor out the x squared, normally we would have this absolute value of x squared times the limit as n goes to infinity, and we would have this 2n plus 3 over 2n plus 5 less than 1, sorry, less than 1 there. But sometimes this causes a little bit of confusion. Absolute value and square roots, they kind of do the same thing. It's just going to guarantee a positive. So I can just leave this as just x squared if I wanted to. And this just becomes 1 right there. So we get less than 1. This becomes 1 because we're looking at the lead coefficients because the powers are the same there. So when I solve this, we're going to get x's between negative 1 and 1. So this is not our interval of convergence, but this says that anything between negative 1 and 1 is guaranteed to converge. So I'm going to go off to the side here. I'm going to start listing out some things I need. So I have my center, which, remember, for the Maclaurin says this is going to be x minus c, so c is just 0 here, so my center is 0. My radius, let's go ahead and list out a radius here as well. The radius, if you remember, comes from right here. So this is saying that the radius is 1, so we're less than 1 when we solve that. So our radius is 1. And now we want to go ahead and find the interval. Now, right now, my interval, it looks like between negative 1 and positive 1, but we do have to check the endpoints, and that's what we're going to do right now. Remember, ratio, and the reason we do that is because the ratio test says if we're less than 1, it's going to converge. greater than 1, we diverge. But it never says anything about equaling 1, and that's where we have to check the endpoints. So let's go ahead and do that. Check the endpoints. My first endpoint is x equals -1. And I'm going to plug it into our series. This becomes from n equals 0 to infinity, -1 to the n. Remember, I'm plugging it into my series up here. That's all we're doing. And then that's going to give us -1 to the 2n plus 1 over 2n plus 3. And let's see what's going to happen here if we plug this in. We're going to get this, and I'm going to kind of clean this up a little bit on top here. -1 to the n. This becomes -1 to the 2n times -1 to the 1. So what we're left with, we get this negative to the 3n right here. And let's see here. So we would get this -1 to the 2n plus 1 right there. Oh, sorry, 3n plus 1. And if we notice, this is still going to alternate. So this is going to be an alternating series, and we can kind of say that this series alternates, decreases in magnitude, and the limit equals 0. Therefore, this converges by the alternating series test. All right. So far for my interval of -1, we can include the -1. Now we have to check the 1 itself. So let's go ahead and do that. Plug in 1 into our series, same thing we would get as n goes from 0 to infinity, -1 to the n, and this just becomes 1 to the 2n plus 1 over 2n plus 3. And that's just 1. We don't have to worry about that. And again, it's an alternating series. So we're going to say the series alternates. We're going to write this a lot in this question. Decreases in magnitude, and the limit equals 0. Therefore, again, this one converges by the alternating series test. All right, so we can include the -1, the +1 as well. And they just wanted our interval right there. So there's everything right there. We have our center, our radius, and the actual interval of convergence. Remember what this says is everything in here will converge on that domain. All right, so let's go to part B. Now, part B, where it's going to be familiar to us. We are told the Maclaurin series evaluated for g at x equals 1/2. So they're giving me a value for x equals 1/2. Now notice 1/2 is in my interval, so it will converge. Is an alternating series. Oh, that's promising. It's an alternating series whose terms decrease in absolute value. So they're telling us an alternating series and the terms decrease. So this is going to converge. Again, they're telling us an alternating series right here. And then they say the approximation for g of 1/2 using the first two non-zero terms, which they tell us is x over 3 minus x cubed over 5 of the series is 17 over 120. So they're saying we're using g to approximate the value of our function here, and we get 17 over 120. We want to show that this approximation differs from the g of 1/2 by less than 1 over 200. So we're trying to find the error. We're trying to show that the error is less than 1 over 200 right here. So we can do that. We can do that really quickly here. Show that the error is less than 1 over 200. That is an alternating series remainder, so we're going to set up our mantra. The series alternates, decreases in magnitude, and the limit equals 0. Therefore, we can say that the error in our series is less than, now don't forget this, if we want it here, we got to get the next term at x equals 1/2. So we already got the first two. We use the first two terms. If we come back up here, we use the first two terms to get 17 over 120. So we use the x over 3, the x cubed over 5. Our next term is this x to the 5th. over 7. So that's what we're going to use. We're going to say is less than, we should use the absolute value, 1/2 to the 5th over 7. Now, let's see what this is. I'm going to kind of clean this up a little bit. This is just 1 over 2 to the 5th times 7, which is going to be definitely less than 1 over 200 by alternating series remainder. And you can, or you can say alternating series error if you like. So take a look at, we've done this a lot of times now. Alternating decrease in magnitude, limit equals 0. So we're setting up the fact that this is an alternating series and it does converge. Therefore, the error must be less than the next term. And remember, what this is really telling us is that the most we can add is this term right here. This is just a side note here. So this is just, let's just put this in red here. This says the most we can add is the next term, which is just the following, which is 1 over 2 to the 5th times 7. And if you want to know what that is just 1 over 224. So the most we can add is 1 over 224, which is less than this 1 over 200. So we're saying that the error that we have is less than the error, than the error that we have is less than the, than the error that we are looking for right here. So we're good. All right, part C. Let's take a look at part C now. So for part C, it says, write the first 3 non-zero terms and the general term on the Maclaurin series for g prime of x. So they just want the derivative of g. So which is easy. That's easy to get. G of x, g prime. Well, we're told g of x is this up here. X over 3 minus x cubed over 5 plus x to the 5x to the 5th over 7. I'm just going to take that derivative. So let's go and do that. We would get 1/3 minus 3x squared over 5 plus 5x to the 4th over 7. And you can get a point just for that, by the way. You can get a point here. And then plus, now it's a series, so they do want the series. So let's take a look up here. So we better put the plus dot up here. Don't forget, we got to put that plus dot. So that's what we're going to do. Plus dot. You might be thinking, Mr. Warner, or whatever, it alternates. Plus, negative, plus, that should be negative. You can make it a plus. It's just plus and negative. That's okay. They'll accept that. That's actually better to write a plus. So, plus, now we got to get the general term. Now, I'm not going to do some fancy work here. I'm just going to come up here and take the derivative here. I'm just going to bring down my x to the 2 and my 2 to the n plus 1. So this becomes, if I take the derivative, we still alternate negative 1 to the n times 2n plus 1 x to the 2n, because if I subtract 1, I just get 2n, and that's going to be over the original, this 2n plus 3 plus dot. You can probably clean that up if you wanted to. I'm not going to worry about that. And there's our answer. Hope you guys enjoyed the video. I'll see you guys later. Bye-bye.